Welcome to video 3.1 over modern atomic theory. Previously in chemistry, we went over in Unit 2 the pre-atomic theory, where we talked about what happened in the 1900s to get us up to today. And so this unit will cover the current model and what we believe to be true about the current atom. And in this unit, we're really going to be dealing with the electrons because all the pre-atomic theory really solidified what we knew to be true about the nucleus, which includes the protons and neutrons. And now, when we get to modern atomic theory, we're really dealing with the electron. And when we talk about the electron, we really use the term quantum. And so you're going to hear in this video and in the next videos to come terms like quantum mechanics and quantum theory. But it all has to do with how the electron is behaving. So in this video, we're going to start to understand this new atomic model. And the guy who led the charge on this was called Niels Bohr. And when we do this, you're also going to have to understand that what we understand to be true about the electron comes with how we see light that is emitted from different gases when they are excited. And so we're going to understand what light is and how this relates to the electron. And when you talk about light, we're also going to have to talk about wave and particle nature. And we're going to talk about things like frequency, speed of light, Planck's constant, and energy. So as we get started, there's a few vocab terms you're going to see. You're going to hear the words like electromagnetic radiation, electromagnetic spectrum, frequency, quantum, ground state, excited state, wavelength, photoelectric effect, and photon. So at any time, if you hear a term, again, if you don't know what it means or if you can't pick it up in context, pause the video, search it on the internet, and then get back to us. So what happened? Well, where we left off, we knew that our protons and our neutrons were in the nucleus. And we believed the electrons existed in that mostly empty space around the nucleus, which took up most of the volume of the atom. However, that model did not really explain in detail what the electrons were doing or give us some information about them. So the current model does not explain how electrons are distributed around the nucleus. So we had to come up with a new model. And this is talking in the last 50 to 75 years. So the main idea here is if the electrons were negative and the nucleus is positive, wouldn't these electrons be attracted to this nucleus and wouldn't they eventually crash down into the center of the nucleus? So that was the thought, and so we had to do some research and understand why is it? Why do these electrons exist in energy levels or energy shells or orbitals? And that's where you come into the guy named Niels Bohr. Niels Bohr had this idea that electrons existed in certain energy states. He said that electrons existed in specific energy states and that for each atom, these guys can be at different energy levels. So as we look at Niels Bohr's model, we're going to watch a quick video explaining a little more about this idea, but we're going to see two possible states that we're going to work with. First, we're going to have the ground state. The ground state is like an energy level, and it's the lowest energy level that an electron can or will exist at. But then what we see here is that there are different energy levels, and we can get these electrons to jump to different energy levels by putting electricity to them or putting energy in form of the heat, however you want to do it. But what can happen is an electron can go from a ground state and jump up to an excited state. So what we're seeing here is there's different energy levels or different energy states. We have the ground state, which is the basic lowest energy level, and then we have excited states, which is a higher energy level or a high excited state. Now, the cool thing about this, and this is how we learned a lot about the electrons, is that when we make an electron jump from the ground state to the excited state by putting in electricity, when it cools off or when it gets too far away or the electricity gets released, it will jump back down to that ground state, releasing colors. So here's a video that we're going to watch in class in its entirety, but I'll put the link in Google Classroom. This video has tons and tons of great illustrations trying to understand what's going on in the quantum world, but let's check this out.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
And so again, what we saw here is that in the Niels Bohr's model, and what he did in the lab, was he saw that when he excited gases in a glass tube, much like neon lights, when those guys were looked at through a prism, he saw these distinct color lines. Oh, if I can find a picture. These distinct color lines. And what's going on here is that the electron will start at a ground state. He puts electricity to it, so it jumps to an excited state. And then when it comes crashing down, when it comes cooling off, it releases energy in these certain specific energy packets. And those energy packets gave off certain colors. And that's how we begin to see this idea of how these different levels exist, because of the different levels, colors that were released are equated to certain energy. Now, to explain all this, you got to go back to physics. You got to understand what is a wave and how our waves and energy and frequencies are related. So part of this lesson is just going to go back to learning what a wave is. So when we look at a wave, we understand that the connection here is that light is a wave. You've also heard that light is a particle, and we'll deal with that in a minute. But light is a wave, and light is a visible part of this, what's called the electromagnetic spectrum. The electromagnetic spectrum just includes all these different energies in our world that are around us at all the time that we might not be aware that are there. Things like radio waves, microwaves, infrared waves, ultraviolet waves, X-rays, gamma waves, and here in the middle is what's called the visible light. So what we're doing here is we're just looking at this electromagnetic spectrum, which is just the range, and we're looking at the different types of electromagnetic radiations, which are the things that radiate, that come off of different energy sources. And so when we understand that light has this wave nature, and we understand light exists in this band of wavelength, we can also now relate that to the energy. But again, as we move on, part of this lesson is remembering what is a wave. So remember, a wave is something that is oscillating. It repeats. There's two kinds of waves. There's one of these that goes up and down, and waves that goes that compress back and forth, which we'll explain more in class. When we look at a wave, we have to understand what wavelength is. Wavelength, again, is just the distance between two peaks or two high parts of the waves or two low parts of the waves. So my wave is just a measurement from here to here. That's wavelength. Frequency, again, is how often a wave occurs. So what you're going to do is you're going to pick a point, then you're just going to count how many waves cross by that point. And so again, some of this should be reviewed. We'll do a lab in class to help you remember this information and experience it. But as we're talking about wave, we just need to understand what wavelength is, what frequency is, and frequency, again, is just how often a wave passes a certain point per second. So what does this do with our class? Well, this does our class because it's going to come to a series of calculations that we have to be able to do so that we can begin to understand Niels Bohr's idea about why what colors we saw relates to how the electrons moved around between the different energy levels. So the first kind of equation we're going to see is the speed of light equation. So here you're going to have to memorize this equation. You have to memorize this constant. This is called the speed of light constant. The speed of light is 3.00 times 10 to the 8th power meters per second squared. And the speed of light has been found to be the wavelength of any electromagnetic radiation times the frequency of that electromagnetic radiation. So remember, wavelength, which is simply the measurement from here to here, and the frequency is how many waves pass per second at a given point. And so we just multiply those two things together, and we get the speed of light. Now, what's cool is if I can measure the wavelength, I can easily calculate the frequency. Or if I know the frequency, I can easily calculate the wavelength because the speed of light is constant. It does not change in our world. So here is a problem that you're going to see and you're going to do in your homework. Suppose a certain type of wave has a length of 2.19 times 10 to the 10th meters. What is the frequency of this wave? So you're just going to use the given equation, and this is a simple algebraic equation, just like A equals B times C. And all you're going to do here is you're going to calculate for one or the other. So in this situation, you're given the speed of light, you're given the wavelength. And so all you got to do simply is divide C by lambda, or in other words, divide A by B to get your C. Again, we'll practice this in class, but this is just like our density problems. It should be pretty self-explanatory. But again, if I take my speed of light, divide by my wavelength, we're going to get our frequency. So now, we just saw and we talked about how light was a wave. Now we're going to talk about how light is a particle. When we say particle, it means it's something that exists, something that has a mass, something that can knock something off of something else. And so this is called the photoelectric effect. The photoelectric effect is this phenomenon that when you expose these certain energies, these certain high energy waves to certain things, that you can see that there's this particle nature where it affects or creates energy or creates sparks. And so what happens is, what we're going to do is we're going to be knocking off electrons. So if I have a high enough energy, or if I have a wavelength with a high enough energy, it's going to be able to knock off electrons. We can see this by putting metal in a microwave. If you go to make some food and you leave your fork in your microwavable dish, you will see the fork begin to spark. I do not recommend doing this. It will tear up your microwave and your mom will get very mad at you, but you probably have seen this before, or you could YouTube it. Or if you just put metal in microwaves in general, it will begin to spark. What's going on here is that the electricity or the energy coming from the waves is knocking off electrons, creating that spark. So what we see here, though, is that there has to be this minimum frequency, which relates back to our equations of a minimum frequency gives me a great wavelength, which we're going to see here has a high energy that can knock off these things. So here's a quick video kind of showing the photoelectric effect. It's kind of cool. So let's watch what happens here. So this guy is charging up this Coke can. He put a lot of electrons. Right now he's creating electrons by static electricity, and he put a lot of electrons right here. What he's going to do now is he's going to reload it back up with electrons, and you see tons of electrons. Tons of electrons are on these pieces of tin foil. Electrons are all negative, so since this is full of electrons, they're going to push away as much as they can. Now this is all connected by metal, so there's tons of electrons everywhere here. We can just see the electrons repel because these tin foils are light enough to where they can push away. Now what he's going to do is he's going to bring out a special kind of light. Now this is actually just a black light, but regular light does not have enough energy. But a black light has higher energy, and that higher energy from those wavelengths are going to gradually knock off those electrons. And as it knocks off those electrons, you see how they left. And when they left, the tinsel fell back down. And this is called the photoelectric effect. So what do we see here? We see light is not just a wave, but it's a particle too. And these particles exist in these small packets called quantums. And each particle of light, we call it a photon. And so as photons come bouncing in, they can knock off electrons. And now here is the relationship to understand the amount of energy, because again, we'll use this to find the energy needed to knock off electrons. So here we go. The question is energy equals Planck's constant times the frequency. Again, Planck's constant is something you have to memorize. 6.62 times 10 to the negative 34 joules times seconds. The new here is called frequency. That's measured in hertz. Hertz is nothing more than seconds to the negative 1 power. So I could put that here just to show you what that looks like. But hertz is just a fancy name of per a second. That's all that is. So now some problems we're going to do in class, and we'll work on this in our homework. And it's going to be like this. What is the amount of energy released by a wave with a wavelength of 5.00 times 10 to the 7 meters? Now notice right off the bat, I have this unit in meters, but if you go back to unit 1, we can see that this could also be referred to as nanometers, 500 nanometers. Again, so this value and this is the same. I just chose to give 2 meters to save you one conversion step for right now. So let's see how this problem would work. If I was to answer this question, I need to know a few things already. First, you need to memorize these two equations. Energy is Planck's constant times frequency. We also need to memorize that the speed of light equals lambda times nu, which again, this is wavelength and this is frequency. So as I read a problem like this, I already have this in my mind. I already know that Planck's constant is 6.626 times 10 to the negative 34. These are things that I just need to know. I need to have these memorized. And we know the speed of light is 3.00 times 10 to the 8 meters per second. So now I know all this information. I feel confident. I feel comfortable. I can read the problem and begin to plug and chug. So first of all, the question asks me, what is the energy release? What is the E? When a wavelength, that's this guy, has 5.00 times 10 to the 7 meters. So I want to find this, and I'm given that. So what you can see here is you have to do some algebra, and this is again is how I want you to do it. You need to combine these two equations by using algebra. So first of all, I see that the frequency here is the same unit in both. So what we're going to do is we're going to solve for the frequency here by doing some simple algebra. Again, how did I come up with this? I divided by lambda. If I divide by one side, I got to divide by the other side. And I simply come up with speed of light divided by lambda equals frequency. Now, since this equals v, I'm just going to substitute this into that equation and come up with my new equation of E equals Planck's constant times C over lambda. Now, this I already have memorized, this I already have memorized, and this was given to me in the problem. So I just plug in my numbers, and I can easily solve any problem like this without stressing out. And again, what goes on the bottom here? That's lambda, 5.000 times 10 to the negative 7 meters. Now when I write all out, I see meters cancel out, I see seconds cancel out, and my answer will be left in joules. So what will my answer be? Well, to find that out, we're allowed to use a calculator in this class. So we take 6.626. I have to use my EE button again, negative 34, times that by the speed of light, which is 3.00 times 8. And then I'm going to divide that by my 5.000 to the negative 7 power. And I come up with this value here. I see that I started with 1, 2, 3, 4 sig figs. My answer will need 4 sig figs. So to get there, I'm going to write 3.976 times 10 to the negative 19 joules. And that answers the question, what is the energy released at this wavelength? So again, this right here is a wavelength. That wavelength has a certain color associated with it. And what they did with Niels Bohr is he saw that color, he was able to do that math behind it and realized the energy between the different energy levels, and therefore he was able to come up with a model for us to see the different energy levels, and that's how we came up to know that there's energy levels in our model. So again, as we see here, why do I know these different energy levels are here? Because I go back and I can see that when a certain color, like 500 nanometers, I think that is the that's the green color. So when a green light was emitted, he knew that was the amount of energy being released, and so he knew that was the energy difference between this energy level and this energy level. And that's how Niels Bohr came up with that new model. So again, what did you see in this video? Light is both a wave and a particle. You see the electrons are emitted, means they're released when an energy hits a metal. So electrons get kicked off when certain energy from certain light hits that metal. And then we see the electrons exist in very specific and discrete energy states. And this, again, is just the beginning of what we're about to do in quantum theory. Have a great day.